I wanted to welcome everyone to the CI Compass Fellowship Program Summer Symposium. CICF is a fellowship program for undergraduate students in the US with the goal of introducing cyber infrastructure and major facilities to students as viable and exciting career options. CICF has two components. We have the spring component, which is a 12-week virtual training program during the spring semester, which is free to any undergraduate students and can also be taken for course credit. During that program, the spring program, students develop technical and research skills important to CI within the context of the data lifecycle at major facilities. The spring fellows also have the option of applying to our summer program, which consists of paid summer positions where students work with CI practitioners on a hands-on project to continue to hone their skills. And this summer, we had students working at MagLab, NCAR, NSO, OOI, UNDERC, and Globus Labs. We're excited for them to share their work, their summer work with us here today. And we're really thankful for all of the mentors at the facilities who worked with our students this summer. Now, if you're interested in learning more about the program, please go ahead and visit our website. I know that Nikki will include that in the chat, or you can email us directly at cicf@ci-compass.org. And then with that, Nikki will take a group photo. Unless Nikki or Eva, did you have anything that you'd like to add also?
No, just thank you everybody for participating, and Angela and Nikki for leading us and leading this effort. Thank you.
Okay, let's get started. All right, our first presenter today is Mahee Shah. So go ahead and take it away, Mahee. You should have screen sharing capabilities.
So, hi everyone, my name is Mahee Shah. I'm currently an incoming junior at the University of Iowa studying computer science, and this was my second summer working with NCAR, the National Center for Atmospheric Research. I had the pleasure this year to work under Catherine Calder on land and ice sheet topography, simulation, and analysis. So this was my poster presentation that I did a week ago. Oh, no, okay. So this was the poster I presented last week at NCAR. And so I'm just going to go a little more in depth about the project I worked on and what I did. So my project was completed mostly on DeRatio. What is DeRatio? DeRatio is NCAR's newest high-performing computing system, which was installed in 2023. So imagine just basically having a super powerful computer that can solve incredibly complex problems very fast. That's what DeRatio does. It's made up of thousands of smaller computers called nodes, each with advanced processors and graphic cards, which work together to perform huge calculations. So this system helps scientists understand and predict changes in the Earth's climate by running detailed simulations. DeRatio is integrated with GLADE, the Globally Accessible Data Environment System at NCAR, which is a powerful storage environment which is designed to handle large amounts of data more efficiently. So it's a unified storage space where researchers can store, share, and access their data across different computational projects and platforms. The three GLADE directories I worked from the most frequently were my homework and Scratch. And on the screen, I included some basic Linux commands that you can use to access like the supercomputer and its basic directories. So this summer, I ran a simulation with the Community Earth System Model, CESM, specifically focusing on the land and ice topography in Greenland. So my project involved studying how the ice sheets in Greenland respond to different climate scenarios over time. So here were the steps that I used to set up my simulation. Step one, I created a new case for the simulation. A case is like a project file that contains all the settings and configurations needed for the simulation. I chose a specific configuration called a TComp set, which is designed to include dynamic ice sheets. And I'm going to talk a little bit more about this later on in my presentation. So step 2 was configuring the simulation. I configured my simulation to run from the year 2015 to 2100. So this involves setting various parameters, such as the length of the run, the type of data the model will use. For example, I used atmospheric data from a previous simulation that forced the ice sheet changes. Step 3 was building the model. So after setting up all my configurations, I built the model, which basically means I compiled all the necessary code so that the computer could run the simulation. This step is crucial because it makes sure that everything is set up correctly before I start my actual simulation. So when the model was built, I ran the simulation on Duratio. And finally, after the simulation was finished running, I analyzed all these results and I used various tools to visualize this data and make it easier to understand and interpret those results. So I'm going to backtrack a little bit and talk about what a T-comp set is. So in the context of CESM, a T-comp set refers to a specific model configuration that is used to run simulations. A comp set or a component set in CESM defines the combination and configuration of various model components such as atmosphere, ocean, land, and ice. So the key characteristics of a T-comp set are T configuration. This setup involves a transient ice sheet component, meaning the simulation includes dynamically evolving ice sheets, typically using the community ice sheet model, CISM. Forcing data. So T-comp sets are often forced with output data from other CESM simulation, such as B-comp sets, which are fully coupled climate simulations. For instance, the T-comp set that I used in my simulation was using atmospheric forcing data from a previous B-comp set scenario. This approach is useful for studying the interactions between ice sheets and the climate system over time, including changes in ice sheet volume and their contributions to sea level rise. So in fully coupled simulations, components continuously interact with each other. For example, the ocean can influence atmospheric conditions, which in turn can affect land, surface processes, and sea and ice dynamics. This integration is kind of crucial and allows the model to capture complex feedback mechanisms, such as how melting ice affects sea level and climate patterns. So in order to analyze all of these results, I had to use plots. So not only I could visualize, but also analyze different trends. Plotting is a crucial step in data analysis because it helps us visualize data, and creating a graphical representation such as line plots, bar charts, and histograms is useful for illustrating trends, patterns, and anomalies in very, very large data sets like the ones that I was using. So here are the steps I used for plotting. First, data preparation. I prepared the necessary data files for the Greenland ice sheet forced by my B-comp set, the SSP5 8.5 scenario data. I ensured all these necessary data sets are available and correctly formatted. Then I set up my environment. So I loaded my necessary Python libraries for data handling and plotting, such as matplotlib and netcdf4. Then the next step was data extraction. I extracted the relevant data from the netcdf4 files, including variables such as ice mass above flotation that I'll reference pretty frequently. And then I created my time series. I created time series data for the extracted variables, so I could analyze changes over the simulation period, which was 2015 to 2100. Next was converting the ice mass changes and sea level changes using appropriate conversion factors, and then performing calculations to derive metrics from this data. And then lastly, I interpreted my results. So I analyzed the plots that I created so I could understand the trends and implications of the ice sheet data and compare the results with our expected outcomes or other scenarios. And I subtracted the plots from each other in order to visualize differences more clearly. So as you can see on the screen on the left, I created 4 different graphs. So I'll explain what each graph means a little bit better. So the first graph is my time series of ice above flotation. So this graph shows the total ice mass above flotation over time. The purpose of this graph is to visualize how ice mass changes from 2015 to 2100 under a specific scenario. And from this graph, we can see that there's a declining trend, which kind of indicates that the loss of ice mass due to increasing temperatures and other climatic factors. The second graph is sea level change due to ice mass loss. So this graph kind of represents the cumulative sea level rise resulting from the loss of ice mass above flotation, which was the previous graph. And the purpose of this graph is to quantify the contribution of the Greenland ice sheet melt to global sea level rise. From this graph, we can see that ice mass loss translates into sea level rise. And this highlights kind of the importance of ice sheet dynamics in sea level predictions. My third graph is the comparison of ice mass change over different periods. So this graph is comparing ice mass changes over different specified periods, for example, 2015 to 2050, 2050 to 2100. The purpose of this graph is kind of to analyze the rate of ice mass change over different periods, and this kind of helps identify periods of accelerated ice loss and correlate them with different climatic events or trends. And the final graph is the annual ice mass loss graph, and this shows the annual loss of ice mass above flotation. So the purpose of this graph is kind of to detail yearly variations and identify any patterns or anomalies in annual ice mass loss. And this kind of provides a closer look at year-to-year changes, which can be useful for shorter term variability in ice sheet dynamics. So the purpose of each graph is kind of to visualize trends and determine whether it's the overall decline in ice mass, the rate of change, or the annual variations. We're also able to quantify impact. So the graphs quantify the impact of ice mass loss on sea level rise and provide a clear linkage between the ice sheet dynamics and global sea level changes. And these visualizations are crucial for kind of interpreting the data from the ice sheet model simulations, so we can understand like future implications of climate change. And so that was what I worked on and some challenges I faced during this project. So I would say my biggest challenge probably was system navigation and configuration. So like I talked about, Duratio is a newer HPC system. It was just recently installed in 2023. And so familiarizing myself with the commands, environment variables, and file system was kind of a learning curve for me. I was working with very large data sets, so I had to make sure that everything was kind of put in the correct directory and I was calling everything correctly. So that took me, I would say, a significant part of my summer to just figure out Duratio. Like I touched on earlier, data management was also an issue, kind of a struggle I had because these data sets were very, very large. And if the data wasn't correctly formatted or placed in like the correct directory, I would just get like little errors and nothing would my case wouldn't build and I just wouldn't be able to run a simulation. And then I would say plotting and data visualization was also one of my bigger challenges because not only did I have to plot the relevant data and make sure I wasn't make sure I was extracting the correct figures that I wanted, but also I had to make sure I was subtracting this data from each other so that I could actually visualize differences and trends and make sure that everything was being handled properly with the correct libraries and stuff. So yeah, despite all these challenges though, this project was a great experience and I learned a lot. So it was awesome to see how I can use what I learned about computer science in school and apply it to real world environmental issues and see it come to life in these plots and the data. So I had a great summer working with NCAR. Thank you.
All right, so I'm Connor Vessely. And this past summer, I've been leveraging machine learning at OOI. So a little bit about me. I'm pursuing a computer science degree at Ball State University. I have a concentration in data analytics and machine learning, as well as a minor in mathematics. And I founded the Computer Science Collective there to help give the resources to other students. I also tutor there. And as far as my professional background goes, I've worked in web development on both the front end and the back end. And last summer, I had the great opportunity to research using machine learning at TAC for my REU. And my future career goals include getting a master's and pursuing a career in research. So a little bit about OOI. The Ocean Observatories Initiative collects ocean data from over 900 instruments. And with that data collection comes data management and data distribution. And so OOI develops cyber infrastructure for the many researchers who use its data. And you can access that data through Data Explorer and through Jupyter Hub, where you don't even have to download the data, which is where I spent most of my summer. And so my main projects, I had 2 projects in computer vision, one with video summarization, and one with digital stills cleanup. And then I also worked on GPU utilization for the newly usable GPUs at OOI. So let's start with that video summarization project. So OOI has nearly 47,000 videos for researchers to use on the Data Explorer and available for download. And so the problem here is that as we can see here, there are some blank thumbnails when they come up, and there are just too many videos to look through all of them. All these like little gray tick marks in this image are a dozen, half a dozen videos, so there's quite a lot going on there, and we need a way to summarize what's going on in the videos and display that to users in a more convenient way. So to solve this problem, I developed a process based on work from a student, a past student from last summer. And so we have a couple parts to this. In order to begin looking at this video, we need to break out images, break out those frames, and extract, in our case, the videos are about 27 frames per second. So I went with every 25th frame to make it a nicer number. So we're grabbing approximately 1 frame every second. And the videos are focused on only a few things at a time, just zooming a bit in and out or panning left and right. The cameras don't move too much, so I thought that was an appropriate number. Not as much camera movement for these videos. And then after that, we need to extract the features from those frames, from those images. And we use VGG16, a really commonly used model for this, to extract those features. And then after that, we performed principal component analysis on those features to make that processing easier. And then we ran those features. Once we had that PCA done, we ran those features through k-means clustering and used 9 groups. And that 9 groups is based on this 3x3 grid of frames. And so that keeps the resulting thumbnail image the same size as the frames so that we can handle those images easier. And so after we get the 9 clusters, we use the central image in that cluster to pick for these 9 representative frames to make into that thumbnail. And this thumbnail will hopefully summarize the video for users in a much more quickly accessible way. One of the priorities here is just telling the users, hang in there. If there's like a black screen here, we'll get to some other imagery in this video. Something maybe more interesting to look at. So one thing that kept coming up during the video summarization project was just the downtime for the feature extraction. It was just taking quite a long time to run many videos at once, and it consumed a lot of memory, making it really impossible to run extremely large batches. So as OOI was getting closer to making the GPUs available, this kept coming up as a test case. So we tried to do the whole process on the GPU, or at least begin the process. So we started with the frame extraction and getting those images out of the video. And the libraries that I tried to use, including Dcord and Torch Vision, had pretty limited support online. So I ended up still, as we got closer to the deadline, I ended up switching to try to use the feature extraction on the GPU, and that was successful. It was very easy to use Keras and TensorFlow on the GPU, just really seamless integration, and it ended up being 2.8 times faster than feature extracting on one video on the CPU. So that's really promising. I'd be excited to learn how that scales for thousands of videos. All right. And then our next project, I did a digital stills cleaning project. And so to explain that, out of tens of thousands of digital still images held by OOI, some of them are not as interesting to researchers. So there are old test images, there's some black photos, and there's some on-land photos like you can see here. And so then the task is to develop a way to identify and flag these images so that they aren't displayed to users. And so since K-means was so successful with the video frames, I thought, why don't we take a look at how it performs on the digital stills? And unfortunately, it wasn't nearly as successful. You can see some of the clusters here. So we can see in that top one, there's one image there that sticks out like a sore thumb. And it seems like it wasn't really clustering well. I tried lots of different optimization techniques on the amount of clusters, but I wasn't able to get the results that I wanted. And so I really, as I couldn't figure this out, I was given the great advice to take a step back and try something simpler, like just identifying the blank images or the black images that we have in the image set. And I was able to do that using good old-fashioned pixel analysis. At first, the obvious solution is to look at the color values and pick out the mostly black images. And so I tried that, and it ran pretty quickly and very, very well, very accurate at that. I wanted to try a different method though as well. So I tried looking at the standard deviation of the pixel colors. Obviously, if there's more variation, there's more colors in the picture, there's more going on. And so that was very successful. It ran a lot quicker, and it has the added benefit of being able to identify blank images of different colors, like maybe a white blank image or something like that. And so that just leaves the problem of identifying the non-C images, which is tasked to the future developer, perhaps using different feature extraction or developing a new model entirely. That is sort of the progress on that and the future for that project. And so I had a fantastic summer with OOI. Want to thank you, send a thank you to the Ocean Observatories Initiative, to CI Compass, and of course the National Science Foundation. And thank you to Jeff, my manager, who's here. Thank you for this summer, for this experience.
All right, then let's get into it. So my name is Matthew Chung, and I did my summer 2024 project with the Globus Labs team and the Parcel team over at UChicago. All right, so the first thing about me, a couple things about me. I'm a second-year computer engineering major at University of California, Riverside. I'm really invested in HPC right now. The picture on the right you see is me and my mentor, Kyle. My internship was remote, but we got to meet up at PERC, which was fantastic, and PERC was a great experience. I'm an Access Campus champion, so I like So I get to like represent my school and do other kinds of things in like the research computing space. I'm the team captain of UCR's Indie Student Cluster Competition team. So we're going to compete at SC this year. I'm also a team captain of a US like national team we're trying to put together for ISC, which is the International Supercomputing Conference in 2025. So I'm just gonna have like a shameless plug that like if anyone's interested in this kind of thing, do reach out to me, or if you're staff or you're like faculty and you know undergrad students at your institution, please do not hesitate to reach out regarding this. And just lastly, I'm the founder and current club president of UCR's High Performance Computing Club. Now that's out of the way, let's get into it. So just to establish some context, so Globus platform is a file transfer ecosystem and platform. It's heavily used in scientific computing and research, especially in most of the major facilities, supercomputing facilities, leadership class, supercomputing facilities. So there's a lot of tools that are used. So there's something called Globus endpoints, which is basically how many researchers transfer their data from supercomputing center to supercomputing center. So it really makes it really easy and quick to just get your data back and forth between various compute resources. But they also have a bunch of other solutions, including compute, which is what my project focused on. There's research automation and predicted data management. Moving on. So more about Globus Compute is it's a function as a service, which means you can run your Python functions and your Python code directly onto supercomputing resources or any other kind of what they call providers, which is either cloud compute resources, NSF facilities, that kind of thing. So what powers that is a parallel scripting library called Parcel, which is based on Python. And the feature that I worked on specifically, I'm working on right now, is regarding elastic scaling. For those who don't know, elastic scaling refers to bring up and provisioning and deprovisioning compute resources to match like workload needs. Typical job schedulers like Slurm don't support this, but this Parcel library does support this via something called pilot jobs. All right, so my project focused on is something called the high throughput executor, which is the core of Parcel when it comes to running jobs on compute nodes. So right now, when tasks come into the queue, they go into the executor, which is then passes those tasks to the interchange, which then moves all the tasks into a first in first out task queue. And it does a little matchmaking between that and the available compute resources, which is in a list called ready nodes. So right now, the current implementation is one where it's using the FIFO task queue and and then they would shuffle the list of ready nodes and just pick a random one. So this does have some benefits, namely that it has very good workload distribution. So all compute resources that have been brought up will see like some workload being applied to this. However, the problem is that in order to scale out or to reduce the node size for jobs that don't actually need it, the workload on those pilot jobs like individual compute nodes needs to be 0, which is highly unlikely given this random distribution method. So my work this summer focused on changing this and updating it to make scaling more feasible and more reliable, as well as not impacting performance that you would see from having the random workload distribution. So my implementation worked on implements two separate things. The first is to add a second task queue, which is a priority queue. So this will take in the priority is based on user labeled runtime information on tasks, which can be passed in on like a per task per function basis. So this will operate in parallel with the FIFO queue. So the reason why we have this is due to the concept of high throughput in the executor. High throughput in this scenario means that thousands of tasks can be processed per second and distributed to the nodes, which is really important when you have like tens of thousands, hundreds of thousands of tasks, and then these all run for a couple seconds, milliseconds, and you just need to keep shoving tasks through. So we want to maintain that performance, but we also want to be able to group the tasks by runtime. So tasks above a certain threshold in terms of runtime will be put into this priority queue. And moving from this queue, will be able to sort those tasks, which means tasks with longer queue times will be grouped together, meaning that when they get assigned to nodes, there's a higher likelihood that the workloads, each task finishes at a similar time. And this works in conjunction with a sorted list, the ready nodes list, which we've now sorted by pilot job or block. So the way Parcel handles this and the way the high throughput executor handles nodes as a resource is take, for example, Slurm, where you usually just submit singular batch jobs with static resource allocations. Parcel can submit multiple of these jobs to either scale up or scale down the amount of resources. So we sort the available nodes by which block they are a part of, and we sort them by the newer blocks first. So older blocks will be able to finish their workloads and get scaled down. So this does improve the scaling behavior just by grouping all the tasks and nodes together in a way that one block gets entirely filled up and leaves other blocks empty for them to get scaled down. And this also, which as you can see so here's an example of the original implementation. So I'm using a benchmarking suite called TAPS to run this, which runs a Cholesky factorization algorithm, which is just some linear algebra stuff. That the purpose of this is that each function has a lot of task dependencies, which shows the variability of a workload of tasks over time. So you can see this is just the random distribution. When tasks come through, they get chosen to be put on a block. So there's only two. The initial amount of blocks you could bring up is 0, and they get spawned. And then, but you can bring up to 4 blocks, but the workload never really needed more than 2 blocks. So I ran this same workload again with the new implementation. You can see how the workload has actually changed. So block 0, which is the first block that comes up first. There's a 5-second polling time in between when Parcel and the high throughput executor checks to see if more capacity is needed. And blocks 1 and 2 are scaled up immediately after when these are ready. And you can see as the x-axis line up, you can see how the resource usage kind of spills over from one block into the other. So you can see that block 0 actually sees very little utilization after the initial burst, which means theoretically it could get scaled down. And this is the benefits of scaling down serve to be as a cost saving and just allowing others to use these compute resources. So because many times a lot of NSF major facilities are based on allocations where you put in an application regarding, you say, I want this amount of compute hours, and they come in the form of service units. So you can get more science done with the same amount of basically resources or currency. So that is basically what I'm working on. Future plans include making this. So the sort by block ID managers has been already added to the Parcel code base, and I'm planning on adding more features as the summer continues. And that brings us to about time. So I want to thank my mentors, Kyle, Ben, Yadu, and Greg for their help on this. And I'd also like to acknowledge CICF and NSF for making this possible. All right, thank you.
So I'm Ingrid Carlson. I'm a rising sophomore at Carroll College, and I'm majoring in computer science and data science, minoring in mathematics and Spanish, and I'm a part of the honors program there. So this summer I had the pleasure of working at NCAR with my mentors Tegan King and Michael Levy. And today I'll be talking about what I worked on this summer, which is automating Cupid with the CESM workflow. So before I get into my project, I'm going to talk about what NCAR does. So NCAR stands for National Center for Atmospheric Research. To expand a bit on what they do, they work on understanding how the weather will change in the future, modeling flooding, exploring the impacts of climate change, developing more detailed air quality forecasts, and researching how the behavior of our sun affects our lives on Earth. At NCAR, I worked in the Climate and Global Dynamics Lab, and I worked remotely this summer, but I was able to come visit last week, and it's really beautiful, and I'm really thankful for this opportunity to work at NCAR this summer. So before I get into my project, the first part of my summer involved learning what CESM was and what Cupid is. So CESM stands for Coupled Earth System Model. It is a fully coupled global climate model that simulates the Earth's climate and all of its components, including atmosphere, land ice, ocean, river runoff, sea ice, and waves. Cupid stands for CESM, Unified Post-Processing and Diagnostics. Cupid integrates time series file generation, data standardization, diagnostics, and metrics from CESM components. Essentially what it does is gather data from a CESM simulation and produce a Jupyter notebook with plots, charts, graphs, tables, and other diagnostics with data from the simulation. So after understanding what CESM and Cupid were, I was able to find a project goal. The goal for this project is to have Cupid run automatically when a CESM case is submitted. So before going into this project too much, I needed to learn a certain set of skills. I first needed to learn what exactly a CESM case is and how to create a CESM case. So a CESM case is a model made up of multiple models that simultaneously simulate the Earth's atmosphere, ocean, land, river runoff, land ice, and sea ice. To create a CESM case, there are 4 steps. First, you need to create your case. Then you need to set up your case. Then you need to build your case. And finally, you need to submit your case. Next, I needed to learn how to run Cupid. To run Cupid, there are 5 steps. The first step is to edit a file named config.yaml to include the user's environment variables. These variables include the case name and multiple file paths. The second step is to change directories into the case directory. This case directory is where Cupid will need to run from. The third step is to activate an environment named Cupid-dev. The fourth step is to run the Cupid run command. This runs the diagnostics. And the last step is to run Cupid build. This command creates the Jupyter notebook with the diagnostics. I also needed to learn how to use PuTTY. PuTTY is a terminal emulator, which allowed me to work on NCAR's high-performance computing machines, Duratio and Casper. And for this project, I mainly used Duratio. I also needed to learn how to use Jupyter Hub. Jupyter Hub allowed me to edit and create files. I also needed to learn how to use GitHub. GitHub allowed me to commit my file changes that I made for this project. And finally, I needed to learn how to code in Bash and Python for this project. So this is a flowchart of how Cupid runs automatically when a CESM case is submitted. So the first step is creating a new case. Creating a new case needs 3 specific arguments. The first is the case name. This is the location of the case and the name of the case. The second is the resolution, which is the model resolution or the grid. And the third is the comp set, which is the component set. Once we create our new case, a case directory will be made. We can do our next steps in the case directory. So next we can set up our case. Once we set up our case, a file named case.cupid will automatically generate. This file is very important for running Cupid automatically. After we set up our case, we can then build our case. And once our case is built, we can submit our case. Once we submit our case, the case.cupid file will run automatically. Then a file named generate will run and generate the config.yaml file. Once the config.yaml file is generated, Cupid can run. There are 3 important parts to this project. The first is the template file, which generates the case.cupid file. The second is the generate file, which generates config.yaml. And the third is Cupid, which processes the config.yaml file and runs automatically. So to go in depth into the template file, this first line here, batch directives, fills case.cupid with machine-specific information based on how the machine is defined in CESM. So for example, the project name, the case name, the user's email, and more. This line of code CDs you into your case directory, which is where Cupid needs to run from. Next, this activates the Cupid dev environment. This line runs the generate file, and this line runs Cupid. So next, the generate file. The way that the generate file generates the config.yaml file is first creating a dictionary from a file named config.template.yaml. This is a template of the config.yaml file. We can then input the user's environment variables into the dictionary. Then the dictionary can be put into a text file, and the config.yaml file can be generated from that dictionary. Finally, Cupid can process the config.yaml file and run automatically. So this work is important to NCAR because first, it allows users to get a quick look at their developmental progress and the progress of their case being run. It also allows users to look at multiple diagnostics. The user can run diagnostics for all components at once unless the user specifies through CompSet specifications. I was able to contribute this work to the CSM workflow. I did this by creating a fork from CCS config CSM repository. This repository is where I made my file changes. I then created a new branch and remote, and then pushed the branch to the fork. I was then able to commit my file changes, and there is a current open pull request for my changes. For the future of this project, we're hoping to move case.cupid to a default workflow. Currently, when we submit the case, we have to specify that we only want to run the case.cupid job. When we move case.cupid to a default workflow, we won't have to specify this. The user can just run case.submit. And we also would like to create a new variable, run Cupid analysis, which will have the value of true or false. And this variable will determine whether or not Cupid will run automatically. I would like to thank NCAR, CI Compass, the National Science Foundation, Brian Dobbins, Mike Levy, Tegan King, my CI Compass professors, and my other fellows. Thank you very much. Are there any questions?
So my name is Lisa Schulz. I am a math major at Cal Poly, and this summer I worked at the University of Notre Dame Environmental Research Center and the Center for Research Computing on a project called LiDAR-based mapping and the parameterization of a hydrological model. So before I start explaining my project, I just want to talk a little bit about why this project matters and why it's important. So UNDERC is in the Northern Highlands Lake District in northern Wisconsin, and it has one of the highest densities of lakes in the world. And a hydrological model will give insight to water and nutrient flows, which is critical to understand the health of this environment. So first I want to give a little introduction to LiDAR data as well, which stands for light detection and ranging data, which was collected by NEON, which is also a major facility across the UNDERC property, which is about 8,000 acres. And it was collected at a 1 by 1 meter resolution. So it's collected by a plane that travels over the area and transmits light pulses to the ground. And the travel time that they take to reflect back to the plane is used to calculate the elevation. So the first part of my project was to construct a DTM, which stands for Digital Terrain Model. And the digital terrain model is a model of the land surface and the elevation data, which can be used in many different things, and which I specifically later used to calculate catchment area and lake elevations. So these are kind of the conceptual steps to get to the DTM. So we start off with point clouds, which come in 1 by 1 kilometer squares. And so each square, we first had to filter out some of the top and bottom points because we had some artificially high and low points before we did that. And then the next step within the function is the ground point classification, which I think can best be described as imagining that the point cloud gets flipped upside down and a piece of cloth is laid over the top, and the points that like hold up the cloth will be the ground points. And then after that, you have to interpolate the rest of the points. And the package that we used in R also has like a variety of methods to do this, which both changed with accuracy and runtime. And we decided to go with the Kriging method, which had a longer runtime, but we found it had the most accurate results at the end. And one issue we faced at this point was also that some of the lakes in the point cloud data were missing a lot of points just because of the way it was collected. Some of the sheen was causing this. And our solution was to use the last catalog functions, which include buffers from surrounding cells, which increased the runtime, but I think in the end it gave us a much better result without any splits. The next part of my project was to create the create a lake water budget model for some of the lakes. So we started with just creating a conceptual model for what we want to do, which you can see by the images there. And we decided to come up, we first had to decide what fluxes we should include that would change and affect the lake volume. And we constructed these equations based on what we thought we could either calculate or what we had data for. And then, so the lake volumes were a state variable, but then we also needed the rates of change of the different soil layer levels and also the water table elevations. So some of the parameters and forcings that we needed came from the UNDERC researchers that collected data there, or they set up the equipment that collected the data. And one of these was the wind speed data that we needed for about 20 years. And we started with over 500,000 observations of wind speed that were taken either at like 10-minute or 1-hour time intervals across many different lakes across the property. So what we first had to do was get those down to 400,000 usable daily averages. And then we eventually got those down to the 7,000 points that we needed for the 20 years. That created a continuous daily time step. Some other data that we needed for the inputs came from the PRISM Climate Group, which is part of Oregon State University, that collects atmospheric data across the whole US and either at daily time averages or also across monthly averages as well. And this includes data like precipitation, air temperature, vapor pressure deficit, and solar radiation. One issue with this was that you first had in R, you first had to download data for the whole US and then slice it down to a 4 by 4 kilometer square of the UNDERC, which took up a lot of runtime, but in the end, the data that we got from PRISM was a lot more, there wasn't as much missing data as some of the UNDERC data. And the accuracy that we lost with using data across the whole property instead of lake by lake was not that much. Some other parameters that we had to get were parameters that we used for the infiltration, which the model that we used for infiltration came from the variable infiltration capacity model. And so we got some of these parameters from the University of Colorado Boulder Water and Climate Research Group. And these were just held constant across time and area. And later when we were testing the model, we had to change some of these as well to fit our data, to fit to fit known volumes better. We also had to get lake-wise data, including like lake surface elevation, lake depth, and things like that. And there were various ways we had to get some of these. For example, UNDERC also had some of these. So I had to go through different data tables to look through and see which ones we could use. And I also had to go back and use the DTM that we created to get some of those lake surface elevations. And then also another skill I learned, I had never used ArcGIS before this, but I had to learn how to calculate catchment areas and perimeters for all the different lakes. So after we had come up with what we thought were all the fluxes that we needed, I ended up having to do a lot of reading about different scientific papers to find equations that we could use for all of these fluxes. And this was definitely a valuable skill for me just because it's not always the first or the second or the third article that had the right information that we needed. And even when we do find a good equation to match our constraints, we sometimes even need to alter it further. And an example of this is for evaporation, the Penman equation on the left is kind of what it starts out with, where you need 7 parameters that need additional equations and 4 data inputs. And then after some reading, I found an article that creates a simplified version of this where only 2 parameters need additional equations and only 3 data inputs were needed without sacrificing any accuracy. And then so in the end, I had the 2 different scripts in R, which one was just reading in the data and matching time steps and interpolating those missing days. And the second one put our final differential equation together and calculated all our forcings and different rates. So I still have 3 weeks left in my project, so I'm still in the process of testing these. And some things that we are doing is comparing to known lake volumes over time and also fitting our constant parameters. So in our preliminary tests, we have to rewrite some equations or get new ones, but we also have to fit those constant parameters as well. So what's next for the project is that if I get this to a good place, it will actually be used by UNDERC researchers. And there's some interest in how water flows can be used to see how different chemicals travel through different lakes, and also how soil water depths and the water table elevation can affect the plants and trees in the area. And if anyone's interested, I have a GitHub repository about some of the code that I created during the summer here, which you can scan. So yeah, I want to thank Dr. Swenson and Dr. Jones for supervising and mentoring me throughout this, and the UNDERC and CRC for hosting, and also CI Compass and NSF for the opportunity and the funding.
Hello, everyone. My name is Ellie Fahey, and I am currently a senior at the University of Notre Dame and a 2023 CI Compass Student Fellow. I am currently studying applied computational mathematics and statistics with a concentration in scientific computing. This summer, I had the privilege of working at the National Solar Observatory Data Center, working in calibrations development, or CalDev, alongside scientists and computer engineers alike. Located in Boulder, Colorado, with a satellite facility in Maui, the National Solar Observatory is a public research institute with the goal of advancing solar understanding and making it possible for scientists worldwide to collaborate on research and development opportunities. In the same office within the University of Colorado Boulder campus is the Laboratory for Atmospheric and Space Physics, LASP, and the National Solar Observatory serves as an association of universities for research in astronomy, or AURA, National Research Center for ground-based solar physics in the United States. I was fortunate enough to spend June working in person at the data center, which allowed me to spend time working alongside the calibrations development team and meeting everyone at the data center as a whole. which was really great. And in addition to this, I joined the CalDev team in meeting with the Hawaiian counterpart to the operation, which are the scientists working on site at the Solar Telescope in Maui. And this is a picture of me and my coworker, Alyssa, in the office. My work this summer was within the DKIS program at the NSO, working on creating the instrument pipelines for the Daniel K. Inouye Solar Telescope. Built and operated by the National Solar Observatory and managed by Aura, the DKIS Solar Telescope collects 7 times more sunlight than any other solar telescope, which is responsible for the highest resolution images of the sun ever taken. Within DKIS is the 150-ton Kude lab, where the sunlight is split and directed into 5 scientific cameras corresponding to the 5 instruments within the physics lab. My work this summer focused on the diffraction-limited near-infrared spectropolarimeter, or DL-NIRSP, which is currently still in its initial stages of developing the data pipeline. Prior to scientists being able to receive the images requested via proposals, the raw data from Maui must first be sent through the data pipelines established by the data center at the NSO in order to make the data more readable and make the necessary calibrations in order to yield the most unobstructed images possible. DL-NIRSP serves the purpose of measuring solar magnetic fields with high spatial and spectral resolution, as well as polarimetric accuracy. This video provided by the NSO illustrates how the observations collected by DL-NIRSP are transformed into visualizable data. Image correction is an integral part of the instrument pipelines, and although it is impossible to eradicate instrument error and other sort of interferences completely, the goal of the CalDev team is to communicate with the scientists at the telescope in order to understand what aspects of instruments may require manual correction. This summer, my task was to write Python code that made corrections to the ramps produced by the infrared cameras in DL-NIRSP. A ramp consists of 1 or more bias exposures, or an exposure with no length, which are used to clear the detectors that are then followed by 1 or more read exposures. Following the read exposures, there are sometimes more bias exposures. During the read exposures, the detector in DL-NIRSP is exposed to light and the signal in the detector is not reset between each read exposure, resulting in the increased signal over the time the detector is turned on, or a ramp. Linearizing a ramp is the process in which the ramp containing multiple files over the exposure time are turned into a single file by taking the final read exposure and subtracting the average of all of the first set of bias exposures from that value on a pixel by pixel basis. I modified the task that was currently in place to linearize the ramp to include a broader range of possible ramps and added in unit testing as needed to ensure the edge cases were still covered. Here you can see, this is an example of what dark frame correction or bias correction can sometimes look like. So you can see that these initial frames are before an image is taken to see what may already be on detectors. And once you are able to correct for that, you get a much clearer image. And on the right here is showing the DL-NIRSP instrument and kind of what it looks like. Here you can see a snapshot of the modified linearized single ramp function with my additions shown on the next slide. So initially, it's the idea of you identify the initial bias frames from the information that are provided within these files that are sent over from Maui. And from there, you find the last read frame and you subtract the data values, the pixel values from the first bias. You subtract that from the last read frame. So here are the changes that I made. The most significant changes I made were writing in a running average. For instance, there are occasions where there's more than one initial bias frame. And when there's more than one initial bias frame, it's important to correct the indexing to grab the last read frame so that you aren't grabbing a read frame from the middle of the read exposures. Once I had my code written within the branch, it was time to move to unit testing, refactoring my code, and integrating these changes back into the Bitbucket pipeline. Each instrument has its own pipeline within Bitbucket, where changes are constantly being made. Git allows them to continuously integrate these changes locally and remain updated while working. After getting expected results using the canonical data prepared by my team, I integrated my work into a branch of the main repository for DLNERSP and Bitbucket. I was working in PyCharm, which is similar to VS Code. It's an IDE that you can use, and it was great because I had not previously worked in PyCharm before, so it was nice to kind of get a look at other IDEs and what that's like working there. From here, I worked to modify my code to pull the necessary information from the local database, which involved me learning and using Redis, and made changes if necessary for the sake of consistency and readability. The code here, which is publicly available, and I link later in the presentation, is very consistent because you want future people that are working that aren't you to be able to go back and make changes and understand, what's going on within this code. Most importantly, I updated the unit test to ensure complete coverage of possible scenarios using PyTest for unit testing. I thought this was a really fun part of my time this summer because it requires you to think about all the possible things that could go wrong. Instead of thinking just about, what you need it to do, you need to think about all the different things that you want to make sure it catches if it shouldn't be doing something so that you don't waste time or money having something run if it's not working. Finally, the next steps in making the data available for use is once my code was added to its file within the DKISS processing DLNERSP repository, which is the pipeline for each specific instrument, it was necessary to make changes to multiple other files that were impacted. So it's kind of a trickle down of, anything that's a new variable that is needing to be referenced that I need to identify within the database and identify across multiple files. So that took some time to make those changes. And after ensuring the unit tests were passing locally, I submitted a pull request for the review and approval of the rest of my team. This involved creating a changelog description that will be published within version updates for the DLNERSP pipeline. And once all the requirements are met on the right here and the pull request is approved, it will be merged into the main branch. I want to thank Nicole, Iwa, Robert Tawa, Alyssa Dirks, Arthur Eigenbrot, Kristen Larson, Fraser Watson, and the entire NSO Data Center for such a unique and enjoyable experience. And I also want to thank them, a majority of them, for coming to watch this presentation. I had a really, really great time. I really enjoyed what I was doing and learned a lot about what it's like to move and process this large scale data. On the left here, you can stay up to date on the instrument pipelines. As code is pushed and versions are updated, you can follow along. And on the right is my LinkedIn profile.
So, hello everyone, my name is Palina, Paliuchenka, and this summer I was interning with Ocean Observatory Initiative at Woods Hole Oceanographic Institute. My internship was remote. So a little about me, I'm a senior doing the SMS program in computer and data science respectively at New Jersey Institute of Technology. And as I mentioned, my internship was remote, but I had an opportunity to go and visit Hui campus and meet OI team in person. And my visit to Hui happened when OI team had their annual meeting. So I had an opportunity, like I said, meet the whole team once again. And I guess I'll start with my presentation. A little bit about OI, as Connor mentioned earlier. OI is Ocean Observing Network that collects real-time data using 900 instruments. And here's a quick snapshot of everything OI does, from instruments to data to their parameters and other stuff. So this summer I worked on 2 projects. Our first project was to implement multiple Jupyter Hub notebooks, and the second project was to analyze trends specifically for El Nino and La Nina event. So for the first project, the purpose of this project was to create multiple templates for scientists or anyone who wishes to use OI data and other programs data inside OI's Jupyter notebook environment without leaving it anywhere. Firstly, I had to familiarize myself with OI environment and their API as I never worked on it before. And then I started to pull in data, and before creating notebooks, I had to familiarize myself what exactly is inside the data, how it's stored exactly, because I never seen such formats before. And later, I started working with a specific pulling data for a specific instrument and parameter using their API. I was working specifically on a global station Papa that is located in Gulf of Alaska. And my instruments was Marine Riser that collects data, and I was focusing just on the temperature data as I just needed to create templates to show how to retrieve data for different parameters and how to work with it. I had to correlate it and plot it and document it so whoever never used the data or Jupyter Notebook can easily understand how to do it. Here's a quick snapshot how OI shares their data. There is a lot of platform. There is a Data Explorer platform where you can go and see their data in different formats and choose which you prefer. And here's a little bit more about the instrument I've been working with. It's a Marine Riser, which is the planking system that anchored to the seafloor. And to stay down, it's connected to multiple anchors to secure it in place. There are lines that are on the right over here. They extend upward from the anchors, and data is collected by this instrument and transmitted to the shore via an acoustic link to nearby gliders. And then those gliders receive the data and relay it to shore stations. And as for positioning, Marines remain under the sea surface all the time until it is retrieved by the team for some checkups and future deployments. Usually OI's deployments last for 1 year until it's retrieved from the bottom. And the next step was to pull data from different scientific organizations that also collect data in this research area. One of those were NOAA-PMAL, which is National Oceanographic Atmospheric Administration, NEON. We've learned about this earlier during our spring fellowship, National Ecological Observatory Network, ONC, which was Ocean Networks Canada, Alaska Observing Systems, and European Ocean Observing System. All of those use different ways of sharing their data. For example, NOAA shares their access to data through the FTP access, and there is no API, you just have to access it. For the NEON, they had their data available through the API and they had tutorials. However, a little bump with the NEON was data was spread by months. And if you wanted to retrieve data from 1 year, you had to access monthly data, which was a little bit time consuming. And for others, ONCAUs, EUs, they were sharing data through the ERDUP, which was easy to access, but due to my minor experience with ERDUP, it was a little bit hard to find the exactly precise data I was looking for, as ERDUP overfilled with different types of data. Sometimes the deployments last for 2 days, 1 week, a year, and it was hard to find what I was looking for. Here are some results that I have achieved from implementing the notebooks. On top, you can see the NEON data from the graphs. It's just their average data to see that it works, that connections are there, and there is no need to leave the environment. As for my personal observation working with different programs, I'd say OI has the most easiest and frequent data, and it's very easy to understand it or even find it on their website. With NOAA, their website was a little bit complicated as you always had to retrieve access, and after some time they would send it to you through the email with links to the website to get it, but it still was easy to access, just required multiple steps. For the NEON, they also had a lot of data. It was a little bit complicated to access it as they had their API, and when you access through the API, you have bunch of links, you get the data, and at the end you just make the link to download your data when you could have gone to their website and get the link from there without the API. And for the ERDOP, as I mentioned earlier, a lot of data, a lot of parameters, but if you're not experienced like me with ERDOP, it's hard to access what you're looking for, the right side, data ranges, parameters, as you have to always open it to see what's inside. And for my second project, I was doing trend analysis specifically for El Niño, La Niña events. But I think before I jump into this, I want to introduce everyone what it is, as it is something that I've learned myself. El Niño, La Niña was first observed in 1600. And in translation, El Niño means little boy and La Niña means little girl. So during these events, during El Niño, trade winds are weakened and warm weather pushes back to east toward the west coast of America. And it affects our weather significantly, meaning that warmer waters cause the Pacific jet stream to move south of its neutral position, and such shift can cause drier and warmer than usual in areas of northern US and Canada. But the US Gulf Coast and Southeast in these periods are wetter than usual and have increased flooding. And for La Niña, it is absolutely the opposite of El Niño, and the trade winds are even stronger than usual. They're pushing more warm water toward Asia, of the west coast to Americas, a flow increase, bringing cold, nutrient-rich water, and such event can cause droughts in the southern US and heavy rains and flooding in Pacific Northwest and Canada. During the La Niña year, winter temperatures are usually warmer. So for the trend analysis, I had to understand the impact of El Niño La Niña events on oceanographic conditions. These events can significantly influence weather patterns, sea surface temperatures, and marine ecosystems. By analyzing those trends over time and correlating them with El Niño La Niña events, we can gain some insight into their effects of the region, oceanographic and ecological conditions. And as per why, it wasn't done before. So that's why this project seemed very interesting to me. I also had to identify long-term trends in oceanographic parameters, such as temperature, salinity, and pressure, and the wavelength, how big are the waves, to determine how these trends correlate with the event. So the most difficult part to me was to understand how exactly data in El Niño La Niña works, as you're having just one data set on certain part is not enough. To build the events, you have to work with multiple data that is being retrieved from the ocean. And NOAA and CI, they were sharing their template of how to implement your own El Niño La Niña, and they were using multiple data sets. Southern Oscillation Index, sea surface temperature, outgoing long wave radiation. During my time with OI, I was able to outline OI's data over the past 10 years with water temperature and see if it matches the El Niño La Niña events. And I started working with the how big are the waves, as this was another parameter that's very significant for the trend analysis. And here are some of the results. Below is the OI data for the past 10 years. And if you can see, for example, in 2021, we were experiencing La Niña event. And if we look on the graph, the temperature is much cooler than in the years above when we had El Niño, when temperatures are usually warmer. This snapshot was taken also from NOAA, and it starts from 1990. So our area of observation is over here. Yeah. So once the ready to go? Okay. So once I add the wave, how big are the waves to the trend analysis, we can see more in depth what exactly is happening there. And for that, we also want to examine with using NEON data. They collect their data in Carroll Creek, which is on the land, but there is a small creek that passes by, and correlate and see the differences, how it's affecting and how it can be connected, so we can do our further analysis. So from this internship, I've gained a lot of takeaways and a lot of information. I've learned how to work with files like NetCDF. That's something I've never was familiar with, and ZAR files I was able to create my own, as some of the deployments, they last for a year, a month, and to get the perfect data ranges, I had to collect all the files and to retrieve the data. Then I also gained a lot of Python skills. I was using a lot of tools that I've never was familiar before, and it was an interesting experience because sometimes it should be working, but it's not working. I definitely advanced my skills in URDUP. I knew about URDUP for a while, but I never had an opportunity to use it as I did. And I've learned a lot about the data collecting instruments in the ocean. I don't come with any background about ocean science. I have pretty much minor understanding. So it was a lot of learning about how everything is working. I got to learn about new tools and events that I've never heard about. For the difficulties that I experienced was not working with the code and doing some analysis, but more about understanding about data, how to store it, as different programs, different cyber infrastructures, they store their data differently, and they're not always so user-friendly as they're used by scientists, and as long as it works, it works. So it was a good experience of learning how to find certain data and accessing it. And the second one would be understanding data for El Niño, La Niña event. At the moment, I understand it, but not fully, as there are several components that affect it. And lastly, understanding my results, as like I mentioned earlier, I don't have any oceanographic events, so I have some results, I have some patterns, I have some anomalies, but I cannot correlate to exactly what they mean. So I will leave it for someone in the team once they look through my results. And I guess lastly, life for the past week and a half, a lot of has been happening that made me delay to present all my work to my supervisor, and I didn't even have a chance to let him know that. So I should submit all my work tomorrow, as finally everything got stable. And for future, I want to receive my master's degree in data science, and probably after get into the research field similar to my internship, or go for PhD. That's something I haven't decided yet on. Thank you for your attention, and I want to say a huge thanks and acknowledgements to Jeffrey Gladstein, who was my supervisor at OI, and the entire team, CI Compass, and National Science Foundations for this wonderful experience. And that's it.
So my name is Mark Onders. I'm a rising senior at the University of Notre Dame, majoring in applied math and computational statistics with a focus in scientific computing. I was a CI Compass Fellow in 2023, and I did the summer program for CI Compass at NCAR this summer. So my project name for my time at NCAR was Investigating Benchmark Capabilities on Airborne Phased Array Radar Code. My mentors were John Dennis and Sina Brown, who both work within the Computer and Information Systems Lab, more specifically on the Application Scalability and Performance team. So a little bit of background about NCAR. It's the National Center of Atmospheric Research. It's located in Boulder, Colorado. It was established by the National Science Foundation in 1960, and it was actually the first federally funded research and development center. It's a beautiful building. It's got really pretty mountains right behind it. It's nestled right up top. That's it down in the bottom right. And what they do there is world-class Earth system science research. And it's a really nice collaborative atmosphere there. They are always collaborating with different scientists, And I think this is in due part to that they're managed by the University Corporation for Atmospheric Research, which is made up of more than 120 colleges and universities. So a little bit of background on my project. Something that's been ongoing and upcoming at NCAR is the introduction of the Airborne Phased Array Radar System, also known as APAR. This will actually be placed on their C-130 airplane and flown through severe storms such as hurricanes, typhoons, and supercells. And they're going to be able to capture large amounts of observational data in real time, which will be really cool. Down in the bottom left, it's actually me in front of the plane. It's really big. And then in the top right is like a little diagram of what the radar system will kind of be shooting, what it will look like. So the importance of this is that it's going to enable in-flight Doppler radar. Instead of having a stationary one on the ground, they're going to be able to take a meteorological phenomena and fly through it and get data as they do that, which is super important because understanding severe weather events can help save lives. So kind of the what and why of my project. The backbone of the APAR radar will be a chunk of code called Samurai, or formerly known as the Spline Analysis at Mesoscale, utilizing radar and aircraft instrumentation. This was created by Michael Bell at Colorado State University, and it contains approximately 50,000 lines of C and C++ code. This code will actually take in the observations from the radar on the plane, and then it will use a system of mathematical processes to kind of reconstruct wind, heat, and pressure fields, which is pretty state of the art because in past times they haven't been able to add thermodynamic variables, so it was just wind, but now they're going to be able to do heat and pressure as well. And a little more on my team that I was on, the application scalability and performance team. Their main goal is kind of to optimize code performance to allow feedback and also increase data collection. So what this kind of means is that if the radar was first taking a general scan of a big storm and they saw a spike in heat or pressure or something that looked interesting, they'd be able to kind of like scope in and get a better data reading on just that one area instead of doing a broad scan. So one of the tools that they use to work on performance is called benchmarking, and that kind of was the center of my internship. I did 2 different projects surrounding benchmarking. And what that basically means is just timing for code. And so they focus on 2 main things for benchmarking and to work on this performance. The first of this is node usage. One major goal that they've been trying to do recently is to switch from computing on CPUs to GPUs. And this is because of the parallel processing capabilities of GPUs, which just basically means that they're going to be able to run multiple tasks simultaneously across different nodes. It also allows for scalability of large data sets, which is really important because weather data is just massive. It's really big. And in doing this, it'll reduce time and energy a lot. And so if you look to the right, I have a graph called Casper runtimes. Oh, I'm sorry if I forgot to explain, but Derecho and Casper are the 2 supercomputers that NCAR uses. So I was able to do benchmarking on both of those. All right, back to the graph now. If you look at the y-axis, this is coming from the cost function 3D minimize variable, which is just a second counter. And this function is a nonlinear truncated Newton solver, which minimizes the residual. So it's basically just getting down to the number that they want, the most accurate number. And this takes the longest time to run, which is why I chose to benchmark it. So I was able to run the supercell test case, which is the test case that's from previous radar scans that they have in their database that they're using to help build code across CPUs and GPUs that they've been using. So if you look all the way on the left, NCAR used to use the Intel Skylake CPU, which took about 800 seconds. Currently, most of NCAR's code is run on NVIDIA A100 GPU nodes. So you can already see that's about a 8 times decrease between the orange and the yellow. Going forward, I think the H100 NVIDIA GPU node just came out in 2022. It's actually really interesting because I was able to write our team's first run script for the H100 node and run the first code on it. And you can see that it's still even decreasing time as it goes on. So moving forward, they're hoping to put more code and more code onto the H100. Another thing that my team, the ASAP team, uses to measure performance is code acceleration. What this basically means is just to use more efficient coding that improves numerical methods. I was able to see this firsthand this summer with my mentor and working alongside them. John Dennis was my mentor, and he's actually published a paper stating that since he's gotten onto the Samurai code and worked within it, that he's been able to increase the speed of it by a factor of 130. One of the things that he did in my time there, the summer that I got to see, and time before and after, was he rewrote some code that involved the H observation matrix. And so instead of reusing it each time it would go through, he changed it to have explicit storing of the transpose matrix. So if you look to the right, this benchmarking I did on derecho, the y-axis is still coming from the same function, the cost function 3D. And you'll see for the 3 test cases, Typhoon, Supercell, and Hurricane, just with a minor code fix like that, it can affect code speed and speed it up. So before and after was before and after he changed the code. And moving forward, they're going to continue to keep working on the code, which will in turn speed up more and more. So the next project I had this summer was to research continuous benchmarking tools for within Samurai, the code. I was kind of pointed to 2 different frameworks. One was a Catch2 framework and the other was a Google framework. Both were written for C++ code. They were both unit testable and included benchmark macros. So they were pre-built and you just kind of had to modify the CMake files to get them in. The biggest difference between the 2, though, is that the Google framework required a separate benchmark executable and a separate main function, which kind of just means that it would be separate from Samurai and it would have to have its own call. So towards the end of the summer, my mentors tried to help me get this implemented, but we concluded that the Samurai design of code and the lack of modularity made it incompatible with the frameworks. And so moving forward, if I had a little more time, it would probably just be to manually write a script to automate the process, whether it was in Python or C++. So they're looking to do that going forward. Overall, it was a very good experience. I learned a lot of skills that I hadn't had. As I said, I'm an applied math major, and so I've only had experience in Python and R and less computer sciencey stuff and backend stuff. So I got to get some experience in bash scripting, operating in a Linux system, which I hadn't done. I know some other people said that. C++, learning what compiling and building is. It was really nice to be able to work on a team that collaborated using GitHub, because I've had GitHub experience, but not been able to actually collaborate. Submitting PRs and changing code and copying the Samurai code onto my own computer was great. I got experience with high performance computing and running jobs on the derecho and Casper. I learned how to do remote connection to supercomputers, as I just said. And then I also learned scientific presentational skills, as I'm doing right now. And also, if you look to the right, that was me presenting at NCAR remotely just last week. That's my poster. Here are some references for my presentation, the code, and my mentor's paper. And thank you. I want to say thank you to CI Compass and everyone else who made this possible. It was a great experience.
Hello, everyone. So my name is Quan. I'm a 4th-year computer science student at Rochester Institute of Technology. So this summer, I had the amazing opportunity to participate in an on-site 10-week internship at the National High Magnetic Field Lab, commonly known as MagLab. Throughout this presentation, I'll be sharing more about the exciting projects I worked on during my time at MagLab and the key learning and the skills that I gained. I hope you find it as interesting and rewarding as I did. Some brief description about MagLab. MagLab is located in Tallahassee, Florida. It is the largest and highest powered magnets lab in the world. It houses a diverse range of water-cooled resistive superconducting and hybrid magnets, utilizing custom developed hardware and software for their control, protection, and monitoring. The lab plays a pivotal role in advancing our understanding of materials and phenomena through the application of high magnetic fields. MagLab employs both manual and automatic data acquisition workflows, resulting in thousands of data sets that capture the daily health and performance of their magnet system. Traditionally, these data sets are analyzed daily using custom plotting script without any dedicated program for automatically detecting long-term trend in key magnets performance features. To enhance traditional workflows and take advantage of the capabilities offered by machine learning, MagLab is exploring the use of data mining techniques and machine learning programs. The aim is to develop systems that can crawl to the data and communicate critical findings via the workplace app SLAC. So during my internship at MagLab, I had the opportunity to explore several projects, but I primarily focused on 3 main projects. The first project I worked on was the coil-resistant deviation forecasting. The second was the power supply failure prediction program. The third was project I undertook was the audio event classification. I'll dive deeper into these projects in the later slides. A specific example of the MagLab data mining and machine learning efforts is focused on predicting coil resistance changes over time. This was actually the first project I worked on during my time here at MagLab. Some background, let's start with the basic structure of magnets and coils. So magnets are composed of coils that generate magnetic fields when electrical currents flow through them. You can see this image. This is an example of Florida bitter plates that when stacking would make up a coil. The coils are configured in series, so the current spiral down from the innermost to the outermost coil. Also, cold water is pumped through the coils to prevent magnets from overheating. This bottom image shows the 4 resistive coils of MagLab's 45 Tesla hybrid magnets, which would fit inside each other when assembled. Over time, these coil resistances start to deviate due to uses. Typically, the inner coil deviates much more than the outer ones. So from our observation, coil voltage deviation for multiple cells indicates that coils are typically replaced when the deviation exceeds 2 to 3%. There's a strong positive linear correlation between deviation and the hour of magnets used for most individual coil life cycle. This strong linear relationship suggests that we can predict the extent of coil deviation in the future test runs. So from the historical data we have for each magnet cell, our goal is to predict the future behavior of coil resistance deviation. Specifically, we aim to determine when the coil resistance deviation will begin to decrease. This decrease indicates that the coil may need to be replaced. To keep our maintenance schedules proactive, we will report these findings on a Slack channel. This way, the team can take timely action based on our prediction to ensure continued optimal performance of the magnets. To tackle this problem, I focus on building and optimizing predictive software models. My approach involves a combination of various statistical and machine learning techniques, along with hyperparameter tuning and data augmentation methods to enhance model performance. I explore a range of modeling algorithms from traditional statistical methods to deep learning methods. Some of the techniques and frameworks that I use include TensorFlow, Docs, and Optuna. Here's the key outcome of this project. So I successfully developed a software model to predict long-term coil resistance using historical data. These predictions allow MagLab staff to anticipate when coil deviation might exceed acceptable limits and require replacement. For example, here we have a forecast of coil resistance deviation for the next 150 days, specifically for coil A data across all magnet cells, which is critical for understanding how resistance is expected to change over time. I also conducted a comprehensive comparison of different modeling techniques focused on accuracy and computational cost efficiency. This analysis helped identify the most effective and resource effective methods for our specific use case. Let's move on to the power supply failure prediction program. Some background about this. There are numerous features that can influence magnet's performance. It's not just coil voltage that matters, but also other factors like water voltage, water pressure, water temperature, and even the power supply from the city of Tallahassee. To prevent damage, there's a built-in magnet protection system that automatically turn off and power down the system when errors occur. However, the number of features that affect the magnets is vast and challenging to inspect manually. Therefore, we plan to leverage machine learning techniques to analyze historical data and forecast potential future magnet failures. Our objective is to develop a predictive models that can anticipate power supply failures before they occur. By forecasting these failures, we aim to minimize unexpected downtime and optimize our maintenance schedules, ensuring the continuous and efficient operation of the magnet systems. Here is an overview of the work that I conducted on this program. I started by reviewing the existing machine learning model that were in use, specifically focused on those based on recurrent neural network or RNNs. Next, I conducted a detailed inspection of the experimental code. By doing this, I was able to pinpoint specific areas where enhancement could be made, leading to more efficient and accurate model performance. To further optimize the model, I also performed extensive hyperparameter tuning. This involved adjusting various parameters to discover the best combination that would maximize both accuracy and efficiency. This is the summary of the result from my work on this program. One key achievement was enhancing the accuracy of our forecasting model. Through this, I was able to significantly improve the model predictive performance. This involved reducing the validation loss and lowering the MAE, or the mean absolute error, on the test set by fine-tuning hyperparameters and systematically adjusting various parameters. Beyond improving the existing model, I also focus on exploring and documenting potential future improvement. This included researching new methodology capable of handling more complex data sets. My next project was the audio event classification program. Some background about this is recently MagLab acquired a handheld ultrasonic probe device. This probe can detect hazardous conditions by analyzing audio frequencies. One of the key techniques we use with this device is creating a MEL spectrogram. These spectrogram transform audio frequency into images. This is an example of the MEL spectrogram. To fully leverage these, we employ a convolutional neural network, or CNN. So some research have shown that they can also be effective applied to audio event detection. Our objective is to develop a classification model capable of detecting hazardous condition in magnet's operation from audio files. Specifically, we aim to create a model that can analyze a short 1 second audio clip and predict the status of the equipment. For example, the model will classify whether the condition of an equipment is good or bad based on the audio input. this approach allows us to detect issues in the equipment before they become audible for to the human ear. By identifying this problem early, we can take proactive measures to address potential issues before they escalate, ultimately enhancing the reliability and safety of our operation. Here's an overview of the work I conducted on this program. I conducted a thorough inspection of the existing experimental code. Also, based on my review, I implemented modification to enhance both the performance and functionality of the code. These changes aim to optimize the code and address identified issues. I also researched various methods to explore alternative methods to it. The result would be I was able to achieve notable enhancement in model performance and accuracy, leading to more reliable prediction. I also was able to reduce the training time. The training time was reduced by approximately 4 times compared to the previous experimental model. This improvement was primarily due to the implementation of optimized matrix multiplication techniques. Some takeaways throughout this experience, I've gained significant personal and professional growth. I've gained a deeper understanding of time series forecasting and machine learning, which had greatly enhanced my problem-solving skill through hands-on project work. Thank you for your attention, and I'd like to take a moment to extend my thanks to the individual and teams who make this internship experience is truly remarkable. So thank you to David, Julia, and Abigail for guidance and for your guidance and coordination, and also CI Compass Fellowship Program for funding this internship. Thank you.
Everyone, my name is Brandon Lozano, and I've been interning at the SLAC National Accelerator Laboratory this summer. And my project has been utilizing AI to create a more efficient solar electrolysis project. And I've been a material science intern at the Stanford Pulse Institute. So here's just the kind of the agenda of what I'm going to talk about today. So I'm just moving out this share screen bar. But firstly, I'll talk a little bit about the Pulse Institute and where I was placed, my background, my mentor. Then I'll go into electrolysis and solar electrolysis, you know, what it is, what are its like implications, and why is it not already like viable. And then I'll talk about my idea for the summer, which was like the project that I'm actually working on. And so something I'll be tackling is what are neural networks and how can they understand scientific literature. Then, you know, to kind of answer that previous question, I'll talk about word embeddings and give a little crash course on word embeddings. Then I'll talk about the potential advantages of my project, and then what I've learned so far at my summer at SLAC. So the Pulse Institute is a joint institute between Stanford and SLAC in the Energy Sciences Directorate. They do a lot of work in chemistry, specifically like quantum chemistry, X-ray spectroscopy, and theoretical chemistry. I was originally placed with my mentor in the corner, Hao Chen, on a project to synthesize cuprous oxide, CO2O, through electrochemical deposition to use as a catalyst for solar electrolysis. But the only problem with that is that the last chemistry class I took was in high school. That was the last time I was in a lab as well. I just wanted to, on my application, I put that I wanted to do like kind of move into different areas like computational biology or chemistry. But they kind of just put me in a pure chemistry group. So when I told my mentor about this, he was like, oh, okay, that might be a problem because quantum chemistry and the chemistry they're working at is, you know, like PhD level stuff. And I'm like, oh yeah, like I think I remember like electron orbital rings and like stuff like that. So I was telling him, I was like, I definitely have a lot more like computational skills that I could use. And I feel a lot more comfortable with that. And that's what I wanted to do, like computational chemistry or something. And so he brought up this idea, or brought up this past project that a colleague from UC Berkeley had been working on in 2020. They basically used a neural network with, I think, like 800,000 article abstracts and this is like getting into quantum physics, so kind of just like stay with me for a second, but it was to predict new materials that have a greater spin orbit torque than what's called unity. So you don't really like need to understand that, but like just the kind of concept. And so now I'll talk about electrolysis for those who don't know. This is just like a basic overlook. You use a power source right here depicted by the battery that's utilized by the cathodes and anodes to rip apart the hydrogen and oxygen bonded in H2O. The only problem though is that currently natural gas is like the most prolific power source used, which like as you can tell just by looking at these pictures is not really super clean. So here's where solar electrolysis comes into the picture, basically using like solar panels to then change that solar energy into chemical energy to then break apart the hydrogen. And then as you can see in this, I don't know if you can see my mouse, but as you can see in the H, that's where like the hydrogen that gets compressed to be like hydrogen fuel cells. And so this is a hydrogen fuel cell efficiency. As you can see, compared to like the most common ones that we see in like vehicles, lithium ion batteries, the range of fuel cells like goes, you get a lot more range without increasing the size of the battery. And so now my actual summer project. So on the right is just a kind of picture showing like, where the term neural network comes from, rather than the different synapses and action potentials and everything and like a neuron. It's basically all like really, really, really complicated math, like bunch of expressions, equations. But yeah, so this idea was based off of my mentor's colleague at Berkeley. And we were thinking, well, what if we can create a neural network that is able to predict other materials that may be better catalysts than the current like candidate, cuprous oxide? And then furthermore, what if we can even predict other methods of synthesis that will result in more desirable characteristics like a better crystal habit, morphology, or like different levels of surface energy? And then this was a really big issue because copyright is like the enemy of science. How do I get enough, or how do I get access to enough open access scientific literature that this neural network will have enough knowledge? And so that's when I found STORC, the Semantic Scholar Open Research Corpus. I was trying to figure out how to web scrape, hundreds of thousands of abstracts, but I was, having to look a lot into like copyright, open access rules, publisher rules, all that stuff. But then I luckily found this resource that the LNAI Institute had already made for scientific text mining. And so this now has over 100 million research abstracts in many different disciplines and over 13 million like fully parsed research articles. And it was originally downloadable by itself, but now it's integrated into the Semantic Scholar API as like a bulk data set. And so this is where another problem came up, is that they took over 3 weeks to approve my API key request, and we're now in like week 7. So pretty much like half of my internship, I was kind of, just planning and designing and thinking of what to do, but I didn't even have the first kind of like step of the data. But so how do we get like all this literature, how do we get it into numbers? Because, right, computers don't understand like letters, characters, or whatever. It's all converted into like numerical representation. So the key question is, how do we translate words and their semantic relationships into numerical representations with mathematical, that should be relationships? Right. And so here's an idea. What if we represent different words as like higher dimensional vectors? And so like, for example, right here with beer, this is just like a really simple, just to like demonstrate the concept, but it's basically just this vector represents like if there's a letter present or not. So beer has 4 letters, so the first 4 are ones and then the rest is 0. here's a little more like naive, but like still kind of like a valid approach. Sorry, I have to move this. I have to keep moving this little screen share thing. So here we can see like if we're looking at like vowel count approaches, then beer and bear, they're like the exact same thing according to this like vector representation, whereas wine has the vowels in different spots, so it's like, you know, way off to the side. Now, this is the actual key thing that that we want to look at. This is the actual thing like that we are using, not a naive approach. It's a context-based machine learning algorithm made by Google Word2Vec. And so as you can see, like it uses like a sliding window basically of like different words around the target word to like kind of gather context. And so as you can see in this one, beer and wine, and these values are just like random. It's just to, you know, demonstrate. But beer and wine are in the same direction, pretty same or similar like length and everything, and a pretty similar like angle in between them. And so that's kind of like representing that you know, they're both alcohol. We know that they're both alcohol, but in the model, it's basically just saying like these things are related and they're pretty close or similar. Whereas bear now is going, you know, a completely different direction where it would probably be going with a bunch of other words that represent animals. And so how do we use these word embeddings? So once we have these basic vector operations, or once we have these vectors, we can do these basic vector operations like this. This is kind of like it's kind of like the one that inspired like the use of vectors. And so it's like king is to man as queen is to woman. It's kind of giving like the machine context. So like take away the man from king and add woman, you know, what would you get? Queen. That's how we can do like an analogy with like these vectors. But then the actual use would be, you know, what materials would work as better catalysts than cuprous oxide. And then as you can see, it just goes lower in abstraction. And if I went even another step lower, then it would just be like the vector representations of these phrases or words. And so potential implications, it could greatly shorten literature review because you can just feed, you know, literally all or a lot of literature into this machine and then get ideas like from it. It would put less emphasis on like domain expertise because that's another thing that really sucks in like an experiment or working like on a project is that literature review, like you need to know that area. You know, you have to either learn it or already know it to really understand everything. It would be a better workflow between interdisciplinary teams, again, because like now you don't have to have like a team of domain experts. You can have people with different ideas where this thing could really help you out, and also potentially less fruitless experiments, because if you know you're predicting these things based off of knowledge, gathered from the scientific literature, then hopefully you kind of have more insights from other fields and other areas that might, you know, if you had conducted the experiment yourself, you would have not considered another field's like impact on your experiment, and you would just have, you know, experiment that didn't, you know, not necessarily like doesn't matter, but it just doesn't get the like outcome that you wanted. And so unfortunately, I don't have any results yet. I'm still working on this. I've got like another 2 or 3 weeks here at Stanford, and I've had a couple different problems. SLAC and Stanford are kind of weird because SLAC is like a Department of Energy lab, but it's like ran by Stanford. So the high performance computing has been kind of complicated to get in. I'm like in a weird limbo as an intern. Like I'm not a student, I'm not an employee. So I have like some weird kind of different permissions and everything. And then, like I said, no one in my research department has knowledge of computer science or these resources. So it's been like a little difficult with that as well, because they're like just chemists. I was not able to get a work computer since I did not request one. I thought that getting access to the high performance computing center would be a lot easier, but that one's on me for sure. And then just typical problems that just happen. You know, data set download stopped, and my script didn't have a way to like pick up where it left off. I just had to delete everything, retry twice. And that data is like over 1 terabyte. So that's just pretty hard. And then just trying to find the best database solution. What I've learned is that I really love working in science. Learning about science and doing it are like completely different. And it feels really awesome, like contributing to the knowledge of all of humanity. I'm really passionate about research and learning. I had to read, like I said, last chemistry class I took was in high school. So just to really understand what surface energies were, or crystal habit, or morphology, I had to read a lot of research papers, watch a lot of crash course videos, skim through textbook chapters, and attend like all talks given to interns, just to have like a foundation of the sciences that they're doing here. And I have kind of learned like, yeah, I mean, I really love this stuff. I'm definitely going to be self-studying, everything that I've put here. And I've really, really liked working in a laboratory setting. I think SLAC also just has like a really, really good work environment. Everyone's super helpful and friendly. But yeah, I've really enjoyed my time here at SLAC. Right now, I don't know if I would continue in chemistry/material sciences. I feel a lot better like using my computational skills, but as I just said, I definitely still want to learn more about it and study it some more. So yeah, that's my last slide. But yeah, I also wanted to thank everyone for their time, and thank you for NSF and to CI Compass for that great fellowship that provided me a lot of the skills I've used. I've still been like referring back to the CICF like GitHub repository a lot. And so yeah, thank you.
Hi, my name is Cailin Kobe, and today I'm going to be talking about the project I worked on this summer at the Woods Hole Oceanographic Institution. So WHOI is a globally recognized leader in oceanographic research, and I was really fortunate to be involved in a project that contributes to their mission by improving data accessibility for their researchers and employees. And so my project was centered around building a professional dashboard using WordPress, enhanced with some HTML and CSS, and integrating real-time data from Google Sheets. This dashboard served as a centralized resource, providing users with access to critical data sets and a calendar of important events. Over the course of this presentation, I will take you through the objectives, design processes, and challenges and outcomes of this project I worked on. So WHOI has been at the forefront of oceanographic research for decades with a focus on understanding and protecting our planet's oceans. My project at WHOI was aimed at developing a centralized dashboard that could simplify the process of accessing and analyzing research data. The dashboard needed to be intuitive and responsive, catering to the needs of the WHOI's researchers who will rely on timely and accurate data for their studies. And so to build this dashboard, I used WordPress as the underlying platform due to its flexibility and robust content management capabilities that WHOI has been using in the past for their website. And so for the layout, I then employed Beaver Builder, which is a drag and drop tool that allowed me to create a visually appealing and functional interface, and then customize that further using HTML and CSS skills that I learned during school, and to make sure it meets the needs of the users. And then I integrated it at Google Sheets and Google Drive, enabling the dashboard to display real-time information critical to ongoing research efforts. So this project was driven by several key objectives. The first objective was obviously to develop a dashboard that was not only user-friendly but responsive, ensuring that it could be accessed on different devices like desktops, tablets, and also only accessible to WHOI members. So we made it that it would be password protected. This was crucial for WHOI researchers who might need access from various locations and devices. Second objective was to integrate real-time data from Google Sheets, allowing the dashboard to always display up-to-date information. This integration was important for ongoing research projects where data timeliness is critical. The third objective was involved providing access to a calendar where the dashboard will keep researchers up to date of important events, deadlines, meetings, conferences, and also for research vessels when they would go off. Finally, ensuring compatibility across multiple devices, and that people could support WHOI's diverse. That I could support WHOI's diverse research activities, whether you're in the office, in the field, or on a research vessel. So kind of taking step by step of how I went about this. The first step was setting up the WordPress environment. I've actually never used WordPress before, and that would kind of serve as the foundation for the dashboard. Again, it was chosen because WHOI uses it for, it's really easy to manage, and it's very ideal for projects that require regular updates and a high degree of flexibility. And then once the WordPress website was in place, I then used Beaver Builder that allowed me to create the initial structure of the dashboard. Their interface made it really easy to lay out the various elements of the dashboard, like data tables, charts, calendar. It is provide a great starting point, but it needed, further customization to meet WHOI's requirements that they need. And that's where I used HTML and CSS, and I wrote my own custom code, and was able to fine tune, adding, features, design, whatever I thought would be appealing. In this, I actually have a screenshot of the actual custom HTML and CSS I used to play. I honestly just kind of use previous information I learned about this and then worked from there. I created, elements such as headers, footers, and responsive features that would adapt seamlessly to what they needed and also different users. The result was consistent and, as a professional appearance that would show the dashboard was not only functional but visually appealing. One of the most important aspects of this was making sure that there was real-time data from Google Sheets into this dashboard. I had to do some research on how I was able to have it be live updated, that if I were to change it in Google Sheets or Google Drive, that it would also update onto the dashboard. And this is where I used the Google Sheets API, which allowed me to just pull directly from Google Drive and then put it onto the WordPress site using an embedded code. This data was displayed then, in various formats like tables, charts, and just made it easy for researchers to analyze and interpret that information. And this integration ensured that, the data was always up to date, which is obviously crucial. The biggest part was the Google Calendar, which I use an iframe, and I actually use an iframe for the entire layout. The calendar was very clear in just providing that there's a clear view of upcoming events, deadlines, and meetings, which my managers were really keen on wanting to see. And obviously that can help them manage their schedules more effectively and just have a communal way of seeing it. The combination of real-time data integration and the calendar made the dashboard, a useful tool for them, enabling them to stay organized and, with minimal effort. Obviously, like any project, there is some fair share of challenges. I would just say, for starters, I didn't really know where to start, as in I've done some web development before, but never used WordPress and Beaver Builder, so that took me some time to kind of figure that out. A big problem was trying to find the data pulled from Google Sheets, which accurately reflect to the dashboard without any delays, that if you wanted to update the website, that everything else would be up to date. And obviously this is really important for researchers. And another challenge was the responsiveness of the dashboard across other people accessing it, making sure that, if you're going to access from a different location, or if you have the password, that makes sure that you're able to get there. I wanted to enter in the code to make sure that it would be able to minimize load times, and that there is cross-platform testing to make sure that there's consistent performance, not just on my computer, but on other people's computers. This involves, testing on the dashboard on different browsers and fixing any issues that would affect, a user's experience and making sure everything was loaded. I think that I was able to create a dashboard that was reliable. This project was obviously a great learning experience for me, both technically and professionally. I got skills that in web development, enhancing my skills in HTML and CSS and APIs, and also, again, using WordPress and Beaver Builder, which are big in web development. It also, helped my problem-solving abilities as I overcome a lot of different challenges along the way, having no clue where to start. I think one of the most rewarding aspects of the project was seeing the end, and that actually all came together, and that, I had a direct impact on WHOI's management and their community. I also learned the importance of collaboration and communication as I worked closely with other team members and asking for help whenever I needed it. And I think overall this experience was great, and it really helped my technical skills, and I think this really opened my eyes to the web development field. I think it made a good impact on WHOI as just having data simplified for researchers, and centralizing the data onto one platform and giving easy to use tools for scheduling that researchers need to perform daily. And looking forward, I guess there are several opportunities enhancing that dashboard's capabilities. Could be expanding the range of data sets integrated into the dashboard, allowing for, more comprehensive data analysis. Another area could be more advanced analytical tools that can give deeper insights into the data, not just, Google Sheets maybe. Obviously, there's always room for improvement to, make the interface more intuitive and user-friendly if I, had more than 10 weeks. I think that those could obviously help and, meet the needs of the community. And yeah, I just want to thank Jeffrey Gladstein, Jim Case, and Hui for a great summer. I honestly really enjoyed this and really got a great experience out of it and learned a lot. And I'm excited to use these skills in my future endeavors. And thank you.